What guides a design? How do we decide what trade-offs to make in a design? Knowing how to do this is a critical skill in engineering design and means that we have to think carefully about design requirements and how they impact our design choices. In a simplified picture of design, design requirements have their genesis in the problem statement provided by the client. It is the client who, remember, could be an engineer and could be in the same or a different organization to you, who has identified the problem to be solved and collected what they believe to be the requirements for the design they are asking you to address. The needs and values they have identified come to the engineer as a problem statement. This is the starting point and is not ready to start focusing on solutions just yet, but rather to focus on what the problem really is and how decisions will be made. So this problem definition stage is where you build up your understanding of the problem through investigation about the industry, previous solutions, existing solutions, and other information. If you're an expert, you have a lot of this ready to go in your mind. But if you are new to an area, you need to have a wide look at the problem and possible solutions. As you build up your knowledge, you can refine the scope and requirements. This is an investigation and reasoning exercise to decide what is relevant and what is most important. This normally requires an iterative approach between the engineer, the client, and major stakeholders. The engineer can move forward once they feel they have a good understanding of the problem and the design requirements are realistic and will be useful for informing the design. The types of requirements specified include the principal functions of the system, which are the actions that must be performed by the system. The constraints, which are the requirements that must be met and put clear limits on a design. These can come from a variety of places, including legal reasons and the requirements of existing systems that your system interacts with. Objectives are the desired attributes or behaviors that we want from the system as a whole. These are not absolute things that must be met, but rather are things that have some sort of quality measure that can be turned into a criteria or a metric. These often initially feature qualitative words like less, more, easy, simple, that point to the things that stakeholders of the system value. These system objectives direct the system design. They are not definitive in what they say the system needs to do. If they were definitive or absolute, they would be constraints, not objectives. Since these are not constraints, we have to decide to what extent we achieve particular objectives. The nature of objectives means that they are never fully achieved. This fact, combined with the fact that many objectives are often competing, means that having objectives normally leads to trade-offs and having to make judgments about the best thing to do. For objectives to be useful, they need to be specific enough to help us make decisions. If they are too vague, they cannot be used to help inform decisions. In addition, the objectives need to be ranked in some way. This is what is needed so that you can weigh up competing objectives against each other. The system objectives supplied by the client are important and form the basis of what the design needs to meet. Using your expertise in research, you may be able to refine the client's objectives, normally by making them more specific. Adding objectives or constraints that were not initially considered by the client. This is part of the expertise engineers bring when they gain experience working on a range of projects. Removing objectives that are found to be unimportant or have no impact on the design. Moving objectives to constraints, if in fact they are things that must be met. Sometimes things can be constraints and objectives. For example, low weight might be an objective, but there could also be a weight limit, making weight both a constraint and objective. You may also find what was given as a constraint is actually a strongly preferred objective. Getting clarity on objectives and the design requirements generally is the most important part of a design. Getting this wrong can be very expensive to fix later on. An example of this is the design of a bridge that could have sustainability as an objective. Whilst this is a good goal for any project to have, it is not a good design objective. It is vague and does not help us make decisions. This could be broken down in a number of ways. Two objectives to make the bridge more sustainable is that it is appealing for pedestrians, so that less vehicles are used, and for better health outcomes for people who use the bridge. Or minimizing the impact on the river is another objective that could be part of being sustainable. This in turn can be broken down into objectives related to the river bed and the mangroves. By looking more closely at this, we find that the mangroves are in fact protected and cannot be disturbed as part of the project. So this is now a constraint for the design. The previous slide is a real example. Here we see the influence of these refined objectives and the new constraints on the design of the Eleanor Chanel Bridge. The pylons are away from the riverbank so that the riverbank with its mangroves is not disturbed. You can also see the cover for pedestrians, which greatly increases their comfort when they use the bridge, particularly in summer. There would have been competing objectives like lowering costs that would have been weighed up against the value of providing that cover for pedestrians. Now we see the very real impact the objectives can have on designs. Our task after identifying and refining objectives is to rank objectives. Clients and engineers are like all people. They like to say what they want, but do not necessarily want to pay for it. This is a problem when designing things. To be able to make real decisions, we need to know which criteria are most important and which are least important. This allows us to make trade-offs and to be able to make decisions. A simple way to do this is to use what is called a pairwise comparison chart. This is a simple tool used to compare objectives. Its strength is that it's simple. And it also forces people to make decisions, which generally people hate doing. In this example table, we have 4 objectives. For the objectives in each row, you compare against the objectives in the column. If the objective in the row is more important than the objective in the column, you put a 1 in that cell. If it is less important, then you put a 0. In this case, we are saying objective 1 is more important than objective 2 and 3, but less important than objective 4. Once you have completed that for a row, you can add up all the ones in the row. Do that for each row, and you'll get a number associated with each objective. These numbers indicate the relative importance of the objective. The higher the number, the greater the importance. In this case, important goes objective 4, then 1, then 2, then 3. This does not mean that 3 has no importance. It just isn't as important as the other objectives. Now that we've established the design requirements, including ranking the objectives, we are ready to make design decisions using these.